Hi everyone, welcome to Dynamics, AP Physics C. This is also known as Newton's laws, and let's start looking at some problems. Okay, let's look at this problem. Conceptual question number 1. An apple is on a table. What are all the forces acting on the apple? What are all the reaction forces to each force on the apple? So this apple, there should be, you might think, oh, this is kind of easy. Force of gravity, force normal. So force of gravity going straight down. And then we have a normal force. The normal force is coming from the table, so we should draw something like this. Okay? Force of gravity is from the center of mass, so it should be right there. But force normal should be coming from the table. Next is, it wants us to do the reaction forces. And maybe I'll do this in a different color. So this is where it gets a little bit tricky, because this is talking about Newton's third law. And what's important to know about Newton's third law is the forces, the reaction forces, are actually on different objects. So the force normal that the table exerts on the apple, there's going to be a force normal that the table feels from the apple. Okay, this is from the apple pushing down on the table, and these are the reaction forces. Okay, force of gravity and force normal aren't the reaction forces. The next thing we should also know is this force of gravity, what's coming from that is actually from the earth. The earth is pulling down on the apple, but the apple is pulling up on the earth. And those are the reaction forces, okay? They're going to be equal, but opposite direction, okay? So I just want to clarify that because usually people get that wrong. All right, moving on. Conceptual question number 2. A person drags a heavy block across the floor by pulling on a rope, shown in the figure below. What are all the forces acting on the block, as well as the reaction forces to each of the forces? So let's look at everything. First of all, we're going to know that there's going to be a force of gravity pulling it down. And then we know that there's going to be a normal force pulling it up, or keeping it up. And then we know that there's going to be a force of friction as it gets dragged. Ooh, not the best picture, but sorry. Force of friction as it's getting dragged. And on the box there, it's being applied. So there's going to be a force of tension that's pulling on it. Now let's draw the reaction forces. So the reaction forces can be a bit more complicated as usual. Remember, the reaction forces are separate from the object. So this force of tension that's pulling on this box, there's also going to be a force of tension going the other way from the rope, okay? As well as the force normal. So this is going to be the block, pushing down on the ground. That's what we're going to call that the force normal, equal but opposite direction. Force of gravity, also like we learned about, this is coming from the earth. I guess I'll just draw here, but coming from the earth, the block is also pulling the earth up. It has so much mass, it barely pulls it up, but it is. And also, the last one, force of friction. So as this is getting dragged, force of friction is going to the left, but this crate, as it's getting dragged, is also dragging the ground, making it go towards the right. So this is, again, Newton's third law. A lot of people get confused with this, so just hoping that that won't be you who's confused. All right, moving on. So simple example here. A box with mass 32.5 kilograms is initially at rest on, and it is acted on by a net force of 14 newtons. The question is, what is the acceleration of the box? Okay, so there's a few things we're going to do here, but the primary thing that we're going to be looking at is we're going to be looking at Newton's second law, which says, sum of all forces is equal to the mass times acceleration. And what we know is the sum of all forces, or the net horizontal force, is equal to 14. The mass of the box is equal to 32.5. And then we're looking for acceleration. So we do a little bit of math. 14 divided by 13.5. 32.5, sorry. And we get 0.43 meters per second squared. Okay. Next part B says, how far does the box travel in 10 seconds? So this is more of a kinematics problem, but we know it starts at rest. So if it starts at rest, initial velocity is equal to 0. We know the acceleration is 0.43 meters per second squared. We know anything else we know? We know, oh, it's going to be traveling for 10 seconds. And now we can find how far it goes by finding the displacement. I'm going to use the equation displacement is equal to v initial t plus 1/2 ax t squared. So we get displacement is equal to 0 plus 1/2 0.43 10 squared. And let me put this into my calculator. 100 times 0.43 times 0.5. And we get 21.5 meters. Okay. Next one, what is the speed of the box at the end of 10 seconds? So good thing is we have a lot of information. So we're looking for the speed at the end of 10 seconds for the velocity final. And we have 4 pieces of information actually. We have v initial, we have acceleration, we have time, we have displacement. So we could pretty much use any formula that has this v final in it. I personally like v final is equal to v initial plus at, so I'll be using that. And then we know v initial is 0 plus a is given as 0.43, and time is given as 10. And then we get 4.3 meters per second. Okay. I hope that made sense, and I hope that wasn't too tough. It should be kind of more of a review of kinematics. Okay, but moving on. All right, 2 adults and a child want to push a frictionless cart in the x direction. The 2 adults push with the horizontal force F1 shown, so F1 100 newtons, 60 degrees, and F2 as shown. So F2 140 newtons, 30 degrees. Find the magnitude and direction the child should push in order for the cart to go directly to the right. So we want this cart to go directly to the right, like this, or this box over here. We want it to go directly to the right, or the cart. So what we should first do, whenever you see problems with angles, most of the time you should break it up into x and y components. So I know F1 of 60 degrees, that's going to be like 77 or something. 100 times sine of 60, that's equal to, 100 times sine of 60. You get 86.6, I was a bit off. So we get this is equal to 86.6 newtons. And then this is going to be sine of 60 times cosine of 60 times 100, which this means this is going to be 50 newtons. Okay, 50 newtons on the x. And now, if we look at the x and y components of F2, so I know that sine of 30 times 140, this is going to be equal to 70 newtons. For the cosine, I don't really know what that is. Cosine of 30 times 140. And we get 121.2. So this is going to be 121.2. So let's kind of write that down. F1x is going to be equal to 50 newtons. F1y is going to be equal to 86.6 newtons. F2x is going to be equal to 121.2 newtons. And F2y is going to be equal to negative 70 newtons because it's going down. So one thing we want to know, the question is, find the magnitude and direction the child should push in order for the cart to go directly to the right, as we see here. So in order for it to go directly to the right, that means the net force in the y direction needs to be equal to 0. So we see that in order for the net force in the y direction to equal 0, the little girl, the force of the girl, she needs to be pushing negative 16.6 newtons, or 16.6 newtons down or south, whatever you want to put it, signifying that it's going down. Okay? And that way, if she's pushing it down like that, that way when they all push together, it'll be moving to the right. Okay? All right, part B now says, if the cart accelerates at a rate of 2 meters per second squared, what is the mass of the box? So looking at all of this, we're going to know that it's going to be accelerating to the right because the little girl is holding it steady. So we should know that all the acceleration is happening in the x direction. So let's look at the forces in x. We have F1 of x plus F2 of x is equal to the mass of the cart times acceleration of the cart. F1 of x is 50. F2 of x is 121.2. Mass of the cart is what we're looking for, and acceleration of the cart is 2. So let's put this into our calculators. And we get mass of cart is equal to 85.6 kilograms. Okay? All right, let's continue moving on. All right, now we're going to talk about mass and weight. So mass is the measure of how much stuff is in an object, how much matter is in an object, how many atoms are in an object. Weight is the measurement of how hard the force of gravity is being exerted on an object. So weight is the same thing as the force of gravity, which is also equal to mass times gravity. That's the main thing to know. Okay, moving on. So on the surface of Jupiter's moon, Io, gravity is 1.81 meters per second squared. A melon weighs 44 newtons on the surface of Earth. What is the mass of the melon on Earth's surface? Let's first look at A. So we know weight is equal to mass times gravity, or force of gravity. Force of gravity is also equal to mass times gravity. And we know the weight of the melon is 44 newtons. We don't know what the mass is, we're looking for that, but we know the gravity of Earth is 10 meters per second squared, or we simplify it to that anyway. So the mass is going to be equal to 44 divided by 10, and we get 4.4 kilograms. Part B is going to be similar. It says, what is the mass and weight of the melon on the surface of Io? What we should know is that the mass stays the same no matter what. The stuff, the amount of atoms, everything like that is going to stay the same. So it's still going to be 4.4 kilograms. However, since there's not as much gravity on Io, we know that the weight is going to be equal to the mass, 4.4, times the gravity of Io, which is 1.81. So the weight's going to be a lot less. 4.4 times 1.81 is equal to 7.96 newtons. Okay? Hope that made sense. Okay, moving on. Normal force. So normal force is the component perpendicular to the surface of the contact force exerted on an object. I like to think of normal force as the amount of contact force. Normal force is not equal and opposite to the weight. It's not always equal. Many times it is, but not always. So just see that it's perpendicular to its surface, as we can see right here. Okay, it's always going to be perpendicular to its surface. Okay. All right, so let's move on. The normal force exerted by the floor is 620 newtons on an elevator passenger who weighs 650 newtons. Is the passenger accelerating? If so, what is the magnitude and direction of that acceleration? All right, so let's look at this problem. It's an elevator problem, which sometimes students have a hard time with, but let's draw it out. So we have this drawing here. We have a person. He's in the elevator. And I'm going to just draw the forces here. So there's a force of gravity on the person, and then there's a normal force on the person. We know that the normal force that the person experiences is 620 newtons, and the force of gravity the person experiences is 650 newtons. Looking at that, seeing that there's more force of gravity than force normal, we should know that the elevator is accelerating downwards. But now, let's try to figure this out. We're going to do the sum of all forces in the y direction is equal to mass times acceleration in the y direction. And we have two forces in the y direction. Force normal plus force of gravity equal to mass of the person times acceleration of the person. Normal force is 620. Force of gravity is negative 650 because it's going down, so I'm going to do minus 650. Mass of the person is going to be 650 divided by 10, so it's going to be 65. And acceleration is what we're looking for. AP, hey. So acceleration of the person, let me just do this. 620 minus 650 divided by 65, and we get negative 0.46 meters per second squared. Okay? And that, just like we thought it was going to be down, it shows that it should be down by a negative 0.46. All right. So I believe the last one we're going to do. A 23 kilogram suitcase is being pulled by a handle that is at an angle of 25 degrees above the horizontal. If the normal force exerted on the suitcase is 180 newtons, what is the force applied to the handle? So let's just draw this out first. So we have the ground here. We have a suitcase here. Let's see. Pulled by the handle that is at an angle of 25 degrees. So there's a force applied, right? Force applied, we don't know what it is actually. Okay, but we do know that the angle is 25 degrees. Normal force exerted on the suitcase is 180 newtons. So we know that this is, drew that kind of crooked. Try to draw it straight. Normal force is equal to 180 newtons. 23 kilogram suitcase. So we should also know that the force of gravity is going to be equal to 230 newtons. And we want to know what this force applied is going to be equal to. Okay. Looks like a little bit of a tricky question, but let's figure this out. So what we should know is we have information in the y direction, so let's figure out what we know in the y direction. So we're going to do sum of all forces in the y is equal to mass times acceleration in the y. We have three forces in the y direction. We have normal force, we have force of gravity, and we have this force applied in the y direction. And this is all going to be equal to the mass of the suitcase times the acceleration of the suitcase. Normal force we know is 180. Force of gravity is negative 230. Force applied is unknown. We don't know what that is. We know the mass is 23. And we should know the acceleration of the suitcase in the y direction is going to be 0 because it's not moving in the y direction. This is all 0. So now we can do a little bit of math and we can find what the force of acceleration in the y direction is. We're doing 230 minus 180 and we get 50 newtons. So now we know this side is 50 newtons. However, that's not the force applied. This is the force applied to the hypotenuse. So we should do sine of 25. Whoopsies. Sine of 25 is equal to opposite 50 over hypotenuse f of a. Then we can say f of a is equal to 50 divided by sine of 25. And we get 118.3 newtons. Whoops. Alright guys, thanks for watching. I hope that was helpful to you guys. And I hope you join us for the next one with friction.